Good morning, and hello to my amazing talk on QEMU in UEFI, in case that wasn't obvious. So who am I? I'm Alexander Graf. I'm a KVM and QEMU developer working for SUSE, and I've done things like, for example, the server class PowerPC port, or nested SVM, in case you've been running virtual machines on your AMD machine inside a virtual machine with KVM. I'm slightly at fault on that one. I was one of the founding members of the SUSE and OpenSUSE ARM teams, so I've been involved a lot with ARM things recently, and I did things like the U-boot UEFI support, which got me into the whole UEFI story in general. And this is work that just happened because I happen to know ARM and UEFI a bit. But to figure out what the differences are, imagine you have two systems. You have an ARM system, this is AH64, and an x86 system, this is x86 64. We're not talking 32-bit anymore. If you have these systems and you plug in a graphics card, and then you attach your monitor, and then you boot them up, what happens? Well, your x86 system just works, right? You plug in graphics cards, turn on, and you see a nice logo, and everything just is shiny and great, and your ARM system barfs and basically doesn't do anything because it doesn't know how to talk to that new graphics card. So why does your x86 system know how to talk to that graphics card? Well, that one's easy. The graphics card itself has a small storage space on it called an option ROM, which provides a driver for the firmware that's running on your x86 system. These days, that's usually a UEFI binary. And that firmware is, or that firmware driver is an x86 binary blob. So if you've ever, so back at the Now Connect a couple, like about a year ago, roughly, give or take, Art and me sat down together because a Linaro member started complaining about the fact that they couldn't use, they just recently acquired another company that produced network cards, and they couldn't use their own network cards in their own ARM servers. And they complained about that fact, which I can certainly understand. So we sat down together and figured out what we can do to work around that whole issue. And there have always been ways to work around limitations with option ROMs in the field, but nothing ever got to a place where you could actually use it. So to understand why this really is an issue, let's first take a look at what the difference really is between x86 and ARM. So if you, from a really 10,000 feet perspective, look at them and you just see, well, this is ARM, this is x86, you can see registers. Who of you knows what registers are? Okay, so registers are basically a small storage entity that you can use in your CPU to put data into, to put integers, numbers into, and then you can do operations on those fields. So if you want to do any operation like an add or anything, it has to happen on these, inside of these small buckets. And then you can combine these together, for example, with an add. So every operation happens on registers. And as you can see, x86 has vastly different register names and a different number, and everything just looks different from ARM. If you, for example, want to move, you just want to copy data. You want to copy the contents of this one register into this other register. Ignore the namings. But still, if you just want to do the same operation, really, you want to copy something from one register to another, the operation to it is even called slightly differently. But down here, you can see the instruction stream, the hex codes of what the CPU reads, and you can see that they look vastly different. There's basically no resemblance between one and the other. And the way to make one thing work on another thing, that's what emulators are. And QEMU is a really nice emulator that happens to actually already implement a way to run x86 instructions on your ARM CPU. Or it really actually emulates anything on anything. But let's get to that part. What is QEMU? So QEMU emulates machines, usually, right? Something in your system. But what actually comprises of your system, and what does system emulation mean? So in system emulation mode, QEMU starts and emulates the whole stack of everything that your computer is composed of. It emulates your CPU, it emulates your hardware, every single piece, your devices, everything you have. And because it emulates your CPUs, it also emulates every instruction running on these CPUs, which means it emulates your kernel that's running on that virtual hardware, and it emulates your user space applications that are running on that virtual hardware. And that's what we call system emulation mode in QEMU. There's a really slight trick to that whole thing where you leave the CPU emulation part out and you push that into your host CPU, and that's what KVM is about. But in a traditional sense, this system emulation basically just emulates the full system, everything, hardware, top to bottom, the whole stack. Then there's something called Linux user emulation. With Linux user emulation, what you do is you basically draw the line where you emulate something way higher up the stack. So QEMU goes and emulates the kernel to user space interface called the syscall interface, and basically only converts the structures that are needed from one to the other and the numbers that are needed from one to the other to be able to run a, say, PowerPC big endian guest binary on your x86 host system. So it has a lot of conversion code in there to convert the structures and to convert syscall numbers, and then just invokes the same call that was invoked by the guest binary on the host Linux kernel again. Which is much more lightweight, much faster, and actually more elegant in a way to run code. But that's not what we need, because in a firmware environment, this doesn't help us anything because firmware is different. In firmware, we have this thing called UEFI that's just running on our hardware, and it does something. So who of you understands what UEFI really is doing? That's way more hands than I was expecting. Awesome. Very good. Very good. This is the right audience. So UEFI, what does UEFI do? UEFI basically drives your hardware. It's the first thing, no, not the first thing, but it's the first thing that you see that comes up on your PC. If you boot up your PC, there's small initialization code, and then there's your firmware, your actual big firmware, your UEFI core parts that go and run. And those things have drivers. They have drivers for your block device, for your network adapter, for your graphics card, for your CD-ROM, for everything you have in your system. There are drivers inside your firmware. And these drivers then connect to the UEFI core and can basically talk to each other. This is like a really big bucket of random drivers that can communicate. Now, they cannot just communicate with each other. You can even do fancy things like use your block device to load a payload like, say, grub, to then again have grub access that same storage backend to load another payload like, say, Linux, and then execute Linux and then pass over access to the system into Linux itself. So this blue line means there's a special mode coming in. When Linux boots up, it basically removes most of the UEFI driver parts and just leaves a small piece called runtime services alive. This is UEFI in a 10-second walkthrough. So let's take a deeper look at what happens when a driver gets initialized. So if you have a driver for a, say, disk device, what that driver does is on startup, it calls a function called install multiple protocol interfaces, and it passes a struct to that function. Inside that struct, there are multiple fields. There are fields for evaluating whether a device is compatible with this driver, whether to start the driver on a certain device, but it also contains fields that are just numbers or pointers or something random. Once it's installed, the UEFI core just remembers that there is a driver, and then when now later on something like the PCIe driver goes and finds that there is a PCIe device, it creates a PCIe object and then asks every driver, there we go, asks every driver whether it actually supports that PCIe device, and that one then can say, yes, sure, that PCIe device is actually a PCIe device that I am the driver for and the driver can then go in and say, sure, or it gets started, and then the driver goes and creates a block device inside the UEFI object space. Right. Using a call called install multiple protocol interfaces, where you can basically create an object or attach protocols to an object. And protocols, again, are callbacks into something that you can find. You can find things like, please give me all devices in the system that support block device-like callbacks. And this thing basically implements one of those. But again, you can see that you have multiple callback function pointers and data structures, and again, you don't know which ones are where by definition. It's just part of the specification of what that particular protocol implements. Then your payload, the thing you're running on top of UEFI, goes in and can, for example, find objects that implement block interfaces and call them. So Grub, for example, can go and say, please give me all the block devices you have, which basically means all the objects that have a block protocol attached to them, and then call a read function on those again, which then means it can read data from that block device. Now, how do you put all of that into a virtual context and emulate things? And what are the problems when you're trying to emulate code like this? Well, for starters, the biggest issue is that different CPU architectures have different application binary interfaces, usually as their standard for UEFI. So the application binary interface defines things like the structure layouts and where things are, things like the endianness, which way around to print, to write characters into your memory. So if you take a look at this structure of this particular block structure in memory, then on your x86 system, it will basically look like this. This is a little endian system. It's 64-bit, so everything is 64-bit aligned. And you have just a couple of pointers and a 64-bit number on top. Well, it turns out that on an AH64 system, it actually looks exactly the same. Because the ABI is compatible in this regard between the two architectures. If this was a 32-bit architecture, everything would fall apart. The pointers would be 32-bit long, everything would be differently aligned. But because those two architectures are so similar, the structure just happens to be identical. So there's another nifty corner case, which is padding. So different ABIs, again, have different standards on how to pad things, how to make sure that a pointer, which is the thing you see down there, the reset function callback is a pointer, that a pointer actually starts on a natural boundary. And a pointer in the 64-bit case is 64-bit long, which means it needs to start on an 8-byte boundary. Which it does here, in this case on x86, because we basically take the 32-bit number, write it down to memory, and then leave 4 pieces of memory unallocated or unoccupied, and then we write the pointer into the struct. Those 4 bytes. Well, it turns out ARM does it exactly the same way. So on AH64, that same ABI compatibility is essentially assured. It means, in a nutshell, if you had, imagine you had a CPU that could run ARM code and x86 code at the same time. Everything they keep in memory would look identical. They could basically pass pointers left and right without having issues. There are corner cases to that wouldn't work 100%, but at least for everything we care in the UEFI world about, that would work. You can basically, those two architectures, the ABIs of those two architectures that are used on the UEFI, in UEFI are 100% compatible for integers. So that means that in theory, imagine we had an ARM grub running, calling into an x86 read function. Because the structures are the same, the ARM grub can actually find the pointer to the read function, because it knows exactly the offset that read function's pointer is at. So it can call it. But what happens on a call, really? I mean, what happens in the CPU when you're trying to call a function? Function calls are actually pretty simple. You have a function and some arguments to it, and what happens is that you basically just take all those arguments, put them into registers. This again is defined in the ABI. And then you take the address you came from, put it on the stack, and you change the address you are at into the new address that you're trying to access, that you're trying to run from now. That's all there is to a call. But imagine that this instruction that you're trying to execute now is an x86 instruction because we loaded an x86 option ROM into our ARM system. You saw earlier that the instruction sets are completely orthogonal, they're completely different. So you couldn't just execute that code, right? It wouldn't work. So we have to do something to actually get us into an emulator at that point. But how do we get into an emulator? We cannot just go and change all the structure callbacks into something different because we don't even know which fields of the structure, which fields of the, it's okay? Which fields of the structures are pointers at which ones are data, because the structures can contain any random piece at any random point. It's not fully random. We could create a huge emulator that knows every single protocol there is in this world and knows all the structures for every single protocol there is in this world, and then tries to replace function pointers with function pointers that trap into the emulator, but that would be insanely hard. So basically Art's trick back then was, why don't we just use this amazing feature called no execute? So modern CPUs have a feature called NX, no execute, that basically allow you to, on certain regions in your memory space, say, well, yes, this region can be read and written, but as soon as somebody's trying to execute code from that region, just don't run this. Tell me about it. This is usually a security mechanism for user space applications. Imagine you have an exploit that tries to put code onto your stack. This mechanism is used to protect the application from such an attack because it basically, the application can then say that my stack, I will never execute my stack, just mark my stack as no execute, so that if somebody tries to attack you through a stack attack, you get a seg fault instead of malicious code executed. But in this case, we can misuse that feature and just say, well, every time we load x86 code, we just mark the region of the code that is x86 code as no execute, which gets us a trap. And on a trap, we can do whatever we want. Now we do know, oh, wow, this application, this thing what is running, was trying to execute x86 code. Let me try to do something about it. So we can swap into our emulation state. We can just execute an emulator at this point that tries to then read that x86 instruction stream and make sense of it. But to do that, well, we were just calling a function, right? So what do these registers actually mean on the other end, which is x86? Well, it turns out x86 again has an ABI, which is slightly different from the H64 ABI for function callbacks, but it's convertible. So what you can do is you can basically take all the registers that are also stored in registers as function callbacks from the ARM side to the x86 side, in this case. Then there's a special thing on x86 where you can only fit 4 parameters into registers. So the 5th lives on the stack, which, well, we can just put it on the stack, that's fine. And then we also put in the return pointer, just fine, and execute the code in UEFI, inside of QEMU, because we can now just simply execute x86 code. But imagine that x86 code is now trying to run ARM code, because it, for example, wants to allocate memory. You can do the same thing again, actually, the same trick. So not exactly the same, but it's a very similar trick. So our emulation code knows which regions are x86. Because it registered them in the first place, right? It knew exactly where it put those x86 binary code pieces. So what it can do is, it can say, oh, well, this x86 code was trying to jump into an address that is outside of the scope I'm actually supposed to emulate in. So it generates a trap internally where we can just move all of those pieces, basically do the ABI conversion backwards again, take all the registers from the x86 state, put them into ARM state, and emulate a function callback on the ARM side. What that gives you is you can basically have a fully chained mode of operation of calls. You can have ARM code, say grub, call into x86 code, say your driver, call into core UEFI code, say memory allocation. And the switch over between where we emulate and where we do not emulate, that one happens on a function level boundary. So you basically now have a system where every single every single function could potentially be either x86 or ARM code, and they both communicate with each other and they just live happily ever after. Biggest question is, does it work? Yes, it does. So this is me. This is me in front of a monitor displaying a picture using a NVIDIA PCIe graphics card on an AMD Seattle system. So that firmware, and this is grub, by the way, if you didn't recognize it. So this is in UEFI. So this is actually displaying something using, so this is ARM grub displaying something using an x86 driver right off the graphics card. So why did we use TCG on that one? There's a couple of reasons why we use TCG. The biggest one for me, for starters, was C. There are a couple of alternatives, like Box, for example, which is C++ code. But if you look at EDK2, which is the core implementation, the reference implementation for UEFI. Oh, right. Andreas was just saying that I should explain what TCG is, which I completely concur with, since it's not quite obvious. TCG is the emulation engine inside of QEMU. So QEMU has used to have a different CPU emulation engine, and now, about 10 years ago, recently, switched over to something called TCG, the tiny code generator. And so this is basically the emulation core of QEMU. So why do we use that part? Well, it's C code, which fits in really nicely with EDK2 because that also is plain C. If you were trying to put C++ code in there, you would suddenly have to start worrying about things like exception handling, which you have to fit into the C model somehow. So that gets complicated. TCG is very well isolated. It was originally written exactly for the purpose of taking an emulator into different projects. So this was originally based on the TCC project, which is the tiny code compiler. So this was used to be the backend for the tiny code compiler, which basically was able to compile Linux on boot within 4 seconds or so. So you could always compile your own kernel when you booted it if you wanted. And then there's another really big one that it's basically most of the core code there is LGPL. And now actually everything we use in this project is LGPL, which means that I'm not going to get into legal issues with GPL code running in an environment that basically is very closed source friendly. I don't want to even remotely be involved in lawsuits of people complaining that their whatever drivers now need to be open source because the firmware can be considered a big general entity and the emulator is part of it, and because that's GPL, it's tainting everything. And TCG supports x86-64. It sounds trivial, but if you look around and you're searching for emulators for instruction sets, you find a dozen at least emulators for 32-bit x86, but good luck finding one for a 64-bit x86. TCG is really 1 out of 3 or so. So how do I use this thing? I guess everybody of you now has their ARM systems at home, with PCI Express, of course, and you want to put your NVIDIA graphics cards in there and just try it out. Or maybe you just run a virtual machine and emulate your ARM system to emulate your x86 code. That's more convenient. Which you can do. There's a GitHub repository was hosted at an ARC's GitHub site called x86 emulator package. And there's a very easy thing to basically compile an OVMF build. OVMF is the firmware you use inside of QEMU if you're running the virtual QEMU machine. If you're running the virtual QEMU machine inside of QEMU on an x86 virtual machine. If you're running on a random host and you're running an ARM virtual machine, then this is basically the binary you're running while you're running that virtual machine. That description is also on the GitHub site, so it's just in the README. But you can see it's actually not hard. You really just do the same thing you would do if you were building your firmware manually, but you also just say, please also refer to this module over there, and everything else is magic. It just works out of the box. I guess you want to see how it works for real, not just with a picture of me standing in front of a screen. I could have faked it, right? So the demo is going to be exactly what I explained. I'm going to run an ARM virtual machine on my x86 notebook, running an option ROM, an x86 option ROM that's passed in using an Intel Ether Express network card. Make sense? Okay. No. There we go. So for starters, we're going to run the emulator, a normal vanilla version without the emulator. So this is basically just going to run a virtual machine, a stock virtual machine with a stock EDK2 firmware that is exactly the way you would find it in your normal distribution. So you can see that it boots up, and it basically shows you, well, that it did find anything. You can look at PCIe, and you can see that it found an E1000E. You see the one? E1000E adapter. So it found the PCI card, and if you look at ifconfig-a-l, you can see that there is no network device at all whatsoever, because the normal OVMF, the normal firmware you're running there, does not contain a driver for that E1000E card, because that usually in a normal environment comes with the card. So if we run the same thing again with a firmware that's compiled with the x86 emulator included, you see one major difference in that the firmware actually goes and tries to boot off of DHCP already, and then loads grub from there, which is an ARM grub. This is exactly the case I was explaining. So this is an ARM grub running on an ARM system, because this is an ARM virtual machine, but the whole network driver, everything it was loading from the network, everything it's doing there, is going through an x86 driver accessing the network card, the emulated network card, but still it's a network card. And then you can just use it and it works, and you basically it feels like a normal driver. You don't even realize that it's x86 code. It's just exactly as if that firmware driver was actually written in ARM code. And speed-wise, you don't even see the difference either. Not going to go through an installation now, but we're open for questions. Thank you. A second up there. There was one hand first.
So you talked about the instructions and data. Do you also take care of that sort of interruptions also?
The question is, we're taking care of instructions and data, and whether we need to take care of interruptions. What do you mean by interruptions? Interrupts?
Yes, maybe some network cards are generating some interrupts to ask some behavior to verify.
Okay. So yes, the question is basically related to interrupts. How do interrupts get handled? Interrupts are always abstracted away in EDK2 and in the UEFI framework anyways, because your device driver does not have direct access to the network, it doesn't even know necessarily what interrupt controller you have, so you always basically just give it pointers and callbacks into what you want to get called. when there's an interrupt arriving, and there's nothing keeping you from running the emulator inside an interrupt context. So you have to think about it, but the conclusion basically is you don't have to do anything about it because it just works. Yeah?
I have two questions. The first one is it only in the firmware that you have to work on that option ROM, or also when Linux is started that it again has to have some sort of emulation because it's calling the option ROM again? And the second question is, do you have any plans to port this to U-boot?
Okay, so two questions. First question is easy to answer. This works during boot time, so basically when you boot up your system, what do you need to do to make... That was the question. Sorry. I just got a sign saying repeat the question. It was the question. So the question is, this works during runtime, during boot time, so basically when your system boots up, but does it also work during runtime? So when your Linux operating system with the blue line, when your Linux operating system is running and threw away most of the UEFI code, UEFI can actually preserve some pieces there and make them available to Linux. The answer is very simple. Yes, it falls apart.
Sorry, can I ask you one side question? You are running QEMU on OS. At least it was on the screen.
Let's defer that to later and first answer those two questions so that we go. I'm terrible at stacking if I get multiple things on top. So yes, it falls apart. Because we basically removed the x86 emulator while from the whole context. So you would now have ARM code calling into x86 code for real. The good news is it never happens because there is basically no support in Linux, at least, for anything that really does runtime services that an option ROM would provide. So it happens by accident. It happens to work by accident, but it is an accident. I do agree.
The Linux never calls into the option ROM in a normal example.
Linux. So the question is, Linux never calls into an option ROM in a normal environment, in normal circumstances. And under normal circumstances, it never calls. Linux never calls into option ROMs in the first place. The only thing that could happen is that the driver registers a special thing for a special runtime service that Linux could call into. And that could happen, but I'm not aware of any Linux drivers that actually do that. Art might know something.
The emulator doesn't support runtime drivers. So one local driver is basically coding itself or something that needs to be designed. You may resonate.
Good point. So Art basically just said that the emulator. So we have code that basically the way the runtime driver would get initialized is that you have another PE binary that gets loaded. And that gets marked as a runtime driver. And we refuse the tag for runtime driver, so it wouldn't even get loaded. It would just refuse to load that driver, but it would mean that things would potentially not work in the way you would expect them to work. I do agree. Was that related to the...
There's a special case in the UEFI spec for network drivers. They can't declare runtime services.
They can?
They cannot declare runtime services.
Oh, okay.
So it's a historical thing back with BBC, which is a whole different regulation.
Yes.
Call open protocol, so even if there was some runtime driver, it would never be able to call it. And porting to
Yes.
that was plenty of my question.
So yes, basically the answer was there's another special case for network drivers that we need to repeat for the recording. There's another special case for network drivers that are not allowed to register runtime services anyways, because there you have that runtime driver thing. And for U-boot, for the U-boot question, the problem is that a lot of, in general, this would be trivial to port to U-boot. But in U-boot, we only implement interfaces that are facing user applications. We are implementing very few interfaces that an actual device driver would use. So for iPixie, we might make it work. But for your NVIDIA network card, that probably uses some PI random callbacks, which we don't even remotely implement. So yes, we could, but does it make sense? I don't think so. Art? Wait. Actually, you know what? You get a microphone. If it works. Well, the button doesn't do anything. If you can make it work, just speak to that. There's a button that doesn't light up, but... All right, let's do it in parallel. Mike and...
Oh.
There you go.
Oh, it works. Okay, so one thing I'd like to add, which is kind of orthogonal to the runtime thing, but it's your Nouveau driver, which is the only driver we have on ARM in Linux, because the proprietary is x86 only, obviously. The Nouveau driver is quite likely to work better if the option ROM has run first. So if the Nouveau driver sees the bare hardware, it might find it in a state that's different from well, what it was tested with. So because it initializes correctly. Well, it's different. It looks different. But it's in the driver.
Yeah. What was that question? Oh, all right, fair enough. More questions?
The test behind the problem you have solved was supposed to be solved by EBC, the UEFI byte code. Whatever happened to it? I probably never seen it.
Oh, he was expecting that. It's in the backup.
The question is, all of this should have been solved by EBC. What happened? If you like to ride dead horses, EBC is a great option. It doesn't even have a compiler as far as I know anymore. It's essentially abandoned. EBC doesn't exist anymore really in the field. There's no option ROMs shipping with EBC, and the problem we were trying to solve is that you have existing devices you want to run. And these existing devices will definitely have x86 option ROMs and basically a zero chance of having EBC option ROMs. So you could either work on with vendors to have an x86 option ROM and an ARM option ROM placed there so that it would run native ARM code if it finds a native ARM system, which already works. Or you could work with them to convert into a completely weird zombie-ish platform that nobody really cares about, which sounds to me like a bad idea.
Yeah.
So it's just died.
I can add a little bit to that, Alex, since I'm Brian. I work on Tiana Core and UEFI and stuff. We had this discussion in the UEFI forum a couple of years ago and had talked about maybe someone can write an EBC interpreter for ARM, because for years there was an interpreter for IE32 and x64 to EBC because it was a problem that Intel kind of created, so we wrote the code, made the compiler. So the only compiler you had was an Intel compiler for an Intel problem. Not too popular in the ARM world for some reason, don't remember why. Oh wait, because, yeah. But at the end of the day, when they looked at it, most of the vendors really wanted to run native code. If they were going to strap a driver to hardware, they would just ask the hardware vendor to give you a native ARM driver. And so you're solving the small corner case problem in the servers where there's not the ecosystem for it. But there wasn't really anybody who wanted to pick up EBC and write it and then have the problem of having a carrier. You would have to carry around two option ROMs anyway, one for EBC and one for x86-64. Well, if you're going to carry two anyway, just make it ARM64 and x86-64 and be done with it.
Right.
So the increase in the size of the firmware is about?
Say again?
The increase in the size of the firmware. So because you entered you added the emulator to grub.
If your firmware is about 10 megabytes and you add 300K, it's not really...
That's the number I wanted to hear. I'm not imposing it's a problem.
I don't remember, to be honest. It was certainly negligible compared to the overall size.
Okay. Just interested in the number.
I did do the benchmarks when I started the port, but I don't remember the exact numbers. Andy, just speak loud. So his question is, how long before this gets merged upstream? There are basically two things blocking this. The biggest thing is that it's using a a framework to trap the PE loader. So we need to basically, when a binary gets loaded, we need to say, well, I know that this is a binary that's not meant for your architecture, but please load it anyways and tell me about it, and then I will fix things up for you. And that interface is not in Core EDK2, and getting this in is, from all I hear, very painful, because you would first have to write about 200 pages of Word documents to actually get things proposed. That's what I heard. But maybe if we can get a shorter route, I'm more than happy to have it. Channel core. If I can just submit a patch and it's in.
It's less complicated than you said, a little more complicated than that.
All right.
Fortunately, you have a lot of beer in this country we can talk about.
That's, beer sounds great. So time's up. Answer is apparently soon. Thank you.